Hello, welcome to lecture 7.1, Fitting Simple to IMU with Optimization. So this lecture is going to be based mostly on this paper, which is called Sparse Inertial Poser, Automatic 3D Human Pose Estimation from Sparse IMUs, which was published at Eurographics 2017, and it actually won the Best Science Paper Award at the conference. So the goal is to be able to estimate the human pose of people based on wearable sensors, little devices that you can place on the body of a person in order to reconstruct the motion. So we want an accuracy that looks similar to the one shown in this video, where here the image is shown for reference, but is not used to produce this result, right? So that's what we want. We want to reconstruct the human pose based only on these wearable sensors. So why do we want this? Because we already showed in the previous lecture how to estimate the 3D human pose and shape from images. We saw, for example, the simplify method. We saw neural body fitting, human mesh recovery from images. So these methods are very useful to analyze people from images in the internet. They are very useful to, for example, to equip robots with a perception module that understands what people are doing in scenes. However, they require an external camera, of course, because they are an image-based method. And this basically makes them limited in the recording volume. You can only record within the volume that is seen from the camera. And some activities cannot be recorded, for example, like biking or skiing or daily activities that require changing rooms. Things like that are very difficult to record with a vision-based system. For this, some people have worked on wearable systems. So for example, like here, this method that was shown by Rodin et al., where you could estimate the human pose based on cameras that were hanging from a helmet. And so this setup was a little bit bulky, but it showed a proof of concept. And more recently, the paper by Denis Thome essentially showed how to reconstruct the human pose based on a camera that is placed on a VR headset that looks at the body from the top. So you get images like this, which are really challenging because you have lots of self-occlusion. And then the challenge is to estimate the human pose. So this allows you to capture human motion outside the fixed recording volume. So this is very useful for that purpose. However, these methods are not very accurate because they rely on these cameras that look at the body from the top, and you have lots of occlusions, and it's still very challenging. It's an interesting problem to work on, an important one, but these methods are still not at the level of vision-based systems. So an alternative is methods based on IMUs, inertial trackers, basically. So an IMU is a device like this little box here that you can place on the limbs of a human person, and then you can capture the motion. As you can see, the standard setups, the commercial setups, require lots of IMUs placed on the body, lots of cables, and they are not very practical because they are very intrusive, right? It takes a long time to set up, and you need a lot of IMUs. But they are not restricted to a recording volume, so this is good. They open new possibilities. But we would like to make this more more usable and more practical. So first, we need to understand what is an inertial sensor. So essentially, it's a little box that contains a magnetometer, and it contains a gyroscope. And from this, basically, it's able to recover the global orientation of this box, or sorry, I should say the local orientation of this box relative to some global coordinate frame. Okay, so what the inertial sensor will give you is a quaternion that maps from the local coordinate frame of the box to the coordinate frame which is defining the global coordinate frame. Now, there's some questions here. First of all, what I said is not completely true, but we will rectify this in a second. So first of all, how do we define the global coordinate frame? So what, for example, like a popular system, which is called XSense do, is like they use the magnetic north detected by a compass. And the direction of the magnetic north is the x-axis. And then the negative direction of gravity, which is measured by the gyroscope. So the gyroscope, sorry, scratch that. An inertial sensor contains a gyroscope and an accelerometer and a compass, okay? And from the gyroscope, you can track the rate of turn, and from this you can derive orientation. From the accelerometer, you can derive acceleration, okay? So essentially the inertial sensor gives you a rotation, right, defined by a quaternion that maps from the local coordinate frame of the inertial sensor to the global coordinate frame. How do you define the global coordinate frame? X is the direction of the magnetic north measured by the compass integrated in the sensor. Y is the negative direction of gravity, which is measured by the accelerometer. So the accelerometer actually measures gravity when the sensor is static, and that defines the negative direction of Y. And then by the cross product, you can figure out what Z should be. So that defines the global inertial coordinate frame. And so the reason I said that what I said is not exactly true is because the inertial sensors do not measure directly the orientation, but they measure the rate of turn, how much you change. And then like there's algorithms that turn this rate of turn and integrating the acceleration and using other like sophisticated algorithms, they can recover like the orientation of the little box. And in addition, you also have the acceleration, which is local to the coordinate frame of this box. It tells you the acceleration measured in the coordinate frame of the box. So essentially, when you're working with inertial sensors, you always have a lot of coordinate frames that you have to deal with. Typically, one is like you have two global coordinate frames. One is the global coordinate frame of the sensor, which is typically denoted as inertial coordinate frame. And this is the one that is defined by this negative gravity and magnetic north. And then you usually have like a global coordinate frame. For example, if you have a vision system with cameras, that's the global coordinate frame of the cameras. Or if you have like the simple model, this might be the coordinate frame of the simple mesh, and so on. So you typically have to figure out what is the transformation between these global coordinate frames. But in addition, you typically want to compare what are the orientations of your model, in this case, for example, simple, right, which are the bone orientations. You want to compare them with the sensor orientations. And so you have two coordinate frames for every limb. One is the bone coordinate frame, and the other one is the actual orientation of the box, right? And the box can be placed in different ways, right? And so you typically have to figure out what this offset is, right? So you will see in this type of papers that there's always like this offset, which is, if things are attached rigidly to the body, is constant over time. All right, so people had basically combined IMUs and vision. So for example, one of my first papers during my PhD thesis was combining multiple cameras and inertial sensors placed at the body. In this case, we were using only 5 to make the system more practical. And then we were integrating the information together in an optimization framework in order to estimate the pose and shape of people. And so this is the key idea, is to combine this vision-based system where localization of joints is more accurate with an inertial tracking that provides good orientation of the joints. And this video illustrates the problems of video-based tracking and how they are solved by combining them with IMU-based tracking. So on the left, you have the video-based tracker, and notice how the arm gets completely twisted. And that's because, like, if you're using image-based losses that depend on, for example, silhouette overlap, like any rotation along the actual direction of the limb, like will produce the same rendering and will produce the same overlap, and therefore it will be very difficult with these image-based losses to recover this actual orientation. But this orientation is very easy to recover from the IMU because this is exactly what is measuring. So this was a little bit the idea. This was the first paper that combined IMU and vision for full body capture. And yeah, so basically that's where we describe the limitations and advantages of each type of approach. So some people also try to go directly from sparse IMU data with some basic machine learning tools directly going to the motion of the full body. For example, like using database lookups, using nearest neighbors. The problem of these methods is that they didn't generalize very well, not only because the algorithm was relatively simple, but also because the databases were also limited. So here we, like in the sparse inertial poser, we took a different approach. So here we take like this analysis by synthesis approach. So we use 6 IMUs placed at the extremities of the body and also the back and the head. And remember that the IMUs provide acceleration, the 3D-dimensional vector measured in the coordinate frame of the sensor, and then the orientation for every one of these sensors. So, so in order to relate body motions to IMU observations, we need an articulated body model of the person to be tracked, right? And we also need to know the IMU positions on the body. That's a requirement. So for the body model, we ended up using SMPL, which had been recently released at that time. And yeah, I don't need to go over what the simple body model is. It takes pose and shape parameters and it produces like a mesh of a person. Importantly here, within the equations of simple, of course, the simple model can also go from pose and shape to the actual orientation of the body part. And this is going to be crucial to compare IMU orientations with the body model orientations. Right, so here we follow an optimization approach, which is consisting of three objective terms. One is the orientation consistency. Then we have an acceleration consistency. And finally, we have a prior, which measures how likely the pose is based on some prior that is built from training data. So here we follow this typical analysis by synthesis. You have observations, in this case, orientation and acceleration. We try to synthesize this orientation and acceleration, and then we compare, and then we minimize the distance between these measurements and these predictions in order to fit the model to the observations. So the this prior on the pose is basically based on this Mahalanobis distance that we described in 2 lectures ago on image-based fitting. And essentially it's like this Mahalanobis distance. And remember, this is the covariance matrix, which needs to be inverted. And this is a quadratic term and so on, right? So remember that this is taking into account the distribution of the data. It makes the assumption that the data is unimodal and follows a Gaussian distribution. And then basically you can penalize this distance in Mahalanobis distance. We also use like joint limits to prevent that, for example, like the elbow completely bends backwards. And these things are crucial because we're using only 5 IMUs. And basically, if you do the math, you will realize that you have less constraints than degrees of freedom. And so we have an under-constraint problem that we need to constrain like by placing prior knowledge. So, okay, so now we need to measure like how consistent is our body model with the orientations provided by the IMUs. And the first question that here arises is to measure the sensor to bone orientation consistency. Bone orientation is the orientation of the model. We need to be able to compute a distance between orientations. And unless you have worked with robotics or computer vision before, you probably are not familiar with distances on SO3. So let me revise a couple of distance metrics in SO3, and let's see how they relate to each other and how we should be careful using them. So the angular distance is perhaps the most natural one. It's the angular distance of two rotations R and S is the angle of the transformation SR transpose. What does this mean? So if I have a rotation S, this represents a coordinate frame mapping to some global coordinate frame, whatever that coordinate frame might be, right? The canonical one. And if we have another rotation R, this also represents some mapping from this coordinate frame to this. So if I now do SR transpose, what I'm getting is the relative rotation between the two coordinate frames, which is what I want to measure. I want to measure how far this frame is from this other frame. So now what you can do is like to consider this axis angle that will bring one coordinate frame or one rotation into another. And that angle about which I rotate along this direction is the result of this angular distance. And it's defined, this is theta, right? And so it's defined as the angle between S and R, that's the same as the angle between SR transpose and the identity. That should be of no surprise because if it has to be a metric on SO3, it needs to be bivariant. This means that if I have to apply a rotation in both sides, like the metric should not change. This makes sense, right? Because if I have two coordinate frames, if I rotate both of them at the same time, the distance between them should not change. It doesn't change, right? As long as I rotate them by the same amount. So I can apply here, to go from here to here, I can apply R transpose in order to get R transpose R, which is the identity. And on the left, I can get SR transpose. And this is equal to the log map, which the norm of the log map. And remember that the log map, we didn't show the formula, but we set in lecture 2, that is, or in lecture 3, maybe, which is essentially giving us the axis angle representation of this rotation matrix, the axis angle representation of SR transpose. And when we take the norm, remember that this scaled axis angle, like the norm of the scaled axis angle, corresponds to the angle, theta. You need to there is some ambiguity because different axis angles can produce the same rotation. So you have to choose the sign of the omega such that the theta is between some specified values, for example, 0 and pi, okay? And this is also called the geodesic, not distance, but distance in SO3. Sorry for the typo. All right, so this is a natural metric for SO3. Another commonly used one is the chordal distance. And the chordal distance is the Frobenius norm, the Frobenius norm of the rotation matrix difference between S and R. So the chordal distance squared equals to the Frobenius norm squared of S minus R. Again, this should be bivariant. I can apply a rotation in both. And so I can transform this into SR transpose minus identity, same trick as before. And now, so that's what it is, right? It's the Frobenius norm of this distance. It's telling you, this is measuring how different from the identity this SR transpose is, right? If you're at the identity, it means that this S and R represent the same frame, same coordinate frame, right? So it makes sense that it takes 0 value when those two equal. Now it's interesting to see that this metric, which is, for example, used to train the simple model, because there we use full rotation matrices, the 9 numbers of the rotation matrix, to modulate the pose blend shapes, if you remember that. So you implicitly use this distance metric, right? In several papers, like people also use directly, they regress directly the full 9 numbers of a rotation matrix, and they use this metric. What is interesting is that there's a direct relationship between this metric and the angular distance metric that I've shown before. So by using the following properties, like the first property is that this is the Rodriguez formula that we saw, that the exponential, which maps an axis angle to a rotation, can be written as the following formula: identity plus omega sine theta plus omega hat squared 1 minus cosine of theta. Remember that this omega hat is this vector, 3-dimensional vector, placed in a matrix that is skew-symmetric. Remember that this is like zeros at the diagonal, and then it's like the matrix equals minus the matrix transpose. Okay, that's a skew-symmetric matrix. Now, if theta omega hat is the axis angle representation of SR transpose, all right, then, and also using the following properties, so that the property that omega hat and omega hat squared are orthogonal under the Frobenius norm, okay, and also using the fact that if you don't believe number 2, just do the math and you will convince yourself. Actually, we will do it in class. There's an intuitive way of looking at this. And then like property 3 is basically that the Frobenius norm squared of omega hat squared or omega hat squared, of omega hat or omega hat squared equals to 2. There's a typo here. They shouldn't be like the squared. Both equal to 2. Why is that? Because, we placed like a unit vector, right? Omega is a unit vector. We placed it in a matrix and we duplicated it one time on the lower diagonal, one part on the upper diagonal. So when we take the squares of everything, we're counting 2 times the norm of the vector. That's why you have these 2. Okay, so now let's use these properties 1, 2, 3 in order to move from this line to this line. The first thing that we should notice is that we plug this equation here. We replace SR transpose by the exponential map. It's the same, right? So we will have like here SR transpose will be equal to I plus omega sinus of theta plus omega squared 1 minus cosine. The identities cancel out. They cancel out, okay? And now I have like this thing here in the equation, right? Frobenius norm squared. We said that omega hat, this is a scalar. Sine and cosines are scalars. So now we have omega hat, which is a matrix, which is orthogonal to omega hat squared. They are orthogonal. Okay. So if they are orthogonal, what happens to the norm of the sum? Well, it's Pythagoras. It's going to be one term squared, this term squared, plus the other term squared. Okay. This is a scalar, so sine squared of theta gets out, right? So of the norm. So I have sine of squared theta. Now the norm squared of omega hat equals to 2. That's why we have this 2. For the other term is the same. The norm squared of omega hat 2 is also equal to 2. That's why this is in this parenthesis. And now we have 1 minus cosine of theta squared, because we're squaring one thing and the other. All right, and then using some basic trigonometry, we arrive at 8 times sinus of squared of theta halves, which can be reduced to the following expression, which is basically 2 times square root of sine of theta halves. And it's interesting because, this is the angle, theta, that's the distance, and this is another distance, which is 2 times some constant times sinus of theta halves, right? So there's a direct relationship of these 2 metrics. Now, another commonly used metric is the quaternion distance. So you could take quaternion 1 S, quaternion 2 R, and subtract them and take the 2 norm, right, of these 4-dimensional vectors. Well, the problem is that a quaternion Q and a quaternion minus Q represent exactly the same rotation. And so this ambiguity needs to be resolved, because here, depending on whether I'm having R or minus R, I would get different distances. This is not what we want. So you need to take a mean over these two possibilities, S minus R and S plus R. So you consider the two signs. And then you take the minimum distance of these two possibilities, and then you're fine. But you have to do this, because otherwise you will run into problems. If you have like a loss in quaternion space that doesn't take into account the sign of quaternions, you'll run into problems during the learning process. And interestingly, there's also a relationship to the angular distance. And this can be seen by considering the following quaternions. One is the quaternion of the identity. Again, what we're going to do now is to write something like this, SR transpose minus I, right? But in quaternions, right? So I is going to be this E, which is like the identity, it's the canonical vector. And then we're going to have like here S times R minus 1, right, which is this SR transpose in quaternion space, quaternion product. This is equal to cosine of theta halves, and this omega, sorry, here this is the V, this is the axis of rotation, V hat, instead of omega, and sine of theta halves. Okay, good. So this basically is the quaternion representation, right, of this this product and this relative rotation. And now let's look at what happens to the dot product as 4 vectors, the dot product, the inner product between these two. Well, only the first part is non-zero, so I'm going to have that this equals to cosine of theta halves. But also, we know that the inner product of 2, 4 vectors equals to cosine of alpha, right? It's a projection of one vector into the other, and that's equals to cosine of alpha, the angle between the two quaternions. From this, it's evident that alpha, this angle between the quaternions is theta halves. Now, why is this useful? Because now let's consider this this metric, which is SR minus 1 quaternion minus the canonical quaternion. This is the same as SR transpose minus the identity. This is exactly the same as S minus R, again, because of this p-variant property. And now we have that these, yes, so now using the fact that this alpha equals to theta halves, we can derive that this quantity here, this distance, equals to 2 sines of alpha halves, and therefore equals to 2 sines of theta fourths. How did we know that? Because we know that the distance of 2 unit vectors, which are separated by an angle alpha, is equal to 2 times the sine of alpha halves, right? It's just basic trigonometry, but we just used here the fact that alpha equals to theta halves. And remember, theta is this angular distance, right? So again, we have like an expression that depends on the sign of the angular distance. So the quaternion distance and the angular distance and the chordal distance, they are all related. And they all depend only on the angle, right? Unsurprisingly, things do not depend on the orientation. They only depend on the angle, right? Okay, so it's important to know what you're optimizing for. So if you're using the angular distance or the chordal distance, the quaternion distance, you're optimizing for different metrics, and they behave differently. So here, there's a plot of how these metrics behave as a function of the angle. So on the y-axis, you have each of the metrics, the angular distance, the chordal distance, and the quaternion distance. So in the y-axis, you have, on the left column, you have d, the distance as it is. And so this is the angular distance, of course, like as it's a linear mapping because the distance equals to theta. And here we have like the chordal distance, which equals to this expression here, which depends on the sign of theta halves. So it decays like this according to the angle. And here we have the Quaternion distance, which notice that decays less quickly. Well, this is telling you a little bit like how the optimization will behave or the learning will behave depending on how close you are to the solution versus how far away you are, right? So this is the distance squared, and notice this creates a quadratic. This creates this sort of curve like here, and so on. All right. So another distance metric is the direct L2 distance in angle axis space. So whenever we're supervising, for example, like the parameters of the simple model on the post parameters, right? Remember this, like, for example, like neural body fitting, where we had this latent loss. That's exactly what they were doing. They were placing an L2 loss on angle axis space. Every time we fit a distribution to the post space of simple, we are assuming, we are adopting this distance metric, right? So let's look at the most naive version. So the Euclidean distance between the corresponding scaled axis angles of log of R and log of S, right? So we take a rotation, we extract the axis angle, we take another rotation S, we extract the axis angle, and we compute the L2 between those two. The problem is that this will be not continuous. Why is that? Because if you take log of R to be the smallest length vector, what can happen is that rotations about angles near pi, about opposite axis, are not close to each other under this metric. For example, like you have this vector and like the positive angle, you land here, and the negative axis, and again, a positive angle, and you land almost there. So they are pretty close. But when I would compute the distance, because they have different signs, the distance would be pretty large. But in the angular distance metric, they would not be far away. So this is a problem, and a problem that it's mostly ignored, at least in the literature in 3D virtual humans. But it's something that might explain why sometimes do not work as well when we work directly in axis angle space during learning. And that's why some papers have proposed to use other representations based on rotation matrices and so on. All right, so there is a solution, which is annoying because you have to take the mean over all possible choice of vectors such that, you know, these two vectors, VR and VS, satisfy that the exponential map of this equals to the rotation matrices. So again, a warning that many regressors to human pose do use this metric, but do not take the mean, which can be a problem for the learning. You can completely confuse the learning system. All right, so now we know a little bit more about how to measure orientation. So in that paper, we chose the angular distance, which is, again, the log of the relative transformation, R bone times R sense. R bone is our prediction, which depends on the parameters of the body model. In this case, the pose. And times the rotation of the sensor transposed, which is the inverse. Now, if we only optimize for orientation consistency, because we have sparse sensors, we only have sensors at the body extremities, this is not sufficient. Because look at what happens. I have here many different poses, okay? But notice that here we have exactly the same orientation of the lower limb, right, lower leg, but the pose is completely different, right? That is telling you that the orientation is not constraining the position of limbs, and it's very ambiguous because you have many solutions that produce the same orientation. There's a manifold of poses that satisfy the orientation constraints, right? Pose different, but orientation measurement nearly identical. So what happens when you optimize for like this pose prior plus the orientation constraint? the following happens. Like you get a motion that looks okay-ish, but not quite realistic. Like the legs don't bend properly and things don't really work so well. And that's because of this ambiguity in the orientation space. So how can we solve this? Well, we have acceleration coming from the sensor. At that time, it was known, but every attempt to use acceleration data before had been a failure. And the reason is that acceleration data is very noisy if we want to compute position, because we need to integrate 2 times the acceleration to obtain position, right? And if we attempt to do this, what happens is that the noise multiplies during this integration and things blow up. And essentially, if you try to just use acceleration alone, this is what happens. It blows up, right? So this alone is not sufficient. But anyways, let's look at how the term for measuring acceleration consistency would look like. Again, like you have the model that predicts the accelerations as seen by the model, and you have the acceleration as measured by the sensor. The first thing to notice is that the acceleration of, the acceleration of the model can be predicted from the positions of a given vertex where the sensor is placed. Let's say that vertex is PT. Using numerical differences, we can obtain the acceleration by applying the following filter: PT minus 1 minus 2 times PT plus 1, right? That's one way of obtaining divided by the dt, which is the delta unit of time. That's one way of it's computing 2 times finite differences in order to obtain the second derivative of position, which is acceleration. And this acceleration predicted by the model depends on the post parameters, because PT and PT minus 1 and PT plus 1 depend on the post parameters. Now, the acceleration given by the IMU also depends on the orientation. This acceleration is measured in the local box, so we need to first transform it into the global coordinate frame by applying this rotation matrix to the acceleration. And then we need to subtract the gravity direction, 9.8 here, because the accelerometer is going to measure all the time the acceleration of gravity, right? We are like, that's what the accelerometer measures, like this. That's why it's called, like, the Earth is like it's like an accelerator, like it's like the gravity is like a system under acceleration. So if you would just drop the accelerometer from a plane, then it would measure 0 gravity, right? Then it would not measure that acceleration, ignoring the friction effects. Anyways, that's a bit confusing, but think about it and you'll realize why. All right. So what happens here? If we use only orientations, we see that there's a manifold of poses that satisfy the orientation constraints. So these multiple legs that are plotted here illustrate multiple pose solutions that satisfy the orientation constraints of the lower limb. So notice there's some, like, a lot of ambiguity because we don't know which one to pick. Now, the idea of this paper and what was the breakthrough that allowed to really leverage IMUs, sparse IMUs to compute human motion, was to optimize for the pose over a batch of frames, such that you can resolve and also integrate acceleration within this batch of frames, such that you achieve 2 things. First of all, you disambiguate these multiple possible solutions by optimizing over all poses at once. And also by optimizing over a batch of frames, you can make the use of acceleration. You're numerically integrating, but using the body model to regularize this numerical integration, which results in much more stable results. So that is one key observation. And the second key observation is that you really want to use a strong body model to constrain this fitting process, because if you don't, we tried, things do not work as well. I mean, they don't work at all, actually. I'm going to show this in the results. So we said that we need to optimize over multiple frames, and this creates an optimization problem that is more complex than the optimization problems that we've seen until now. But we can still solve it. We have here like this optimization, which is a summation over t frames, a summation over the 6 sensors placed on the body and we have this orientation constraint for one for each sensor, which is the angular distance between our orientation prediction and the sensor orientation. We have the acceleration consistency, again, the same summations here, and we have the prior over the pose. So that's the optimization over a batch of frames T. So how do we solve such optimization problem? So we've seen this several times. We consider the vector of residuals E, which basically, if you have n residuals, you have like this as a vector of n entries. And to minimize the scalar E transpose E, we linearize the vector of residuals with the Jacobian matrix. So basically, E plus delta x equals E of x plus the Jacobian times delta x. And this is approximating how the error looks in the neighborhood of x. And now what we can do is use these Levenberg-Marquardt equations or solve this linear system here, E of x plus delta x minus EX, and then solve for this delta x, right? That makes the error as small as possible. All right, so the acceleration residuals, so let's look at the form of this Jacobian matrix, right? For example, for the acceleration residuals. So remember that the acceleration is approximated from the model using this pt minus 1 minus 2 times pt plus 1. And this will show up in the Jacobian computation of the acceleration term. So you will have like g Jacobian minus 2 times Jacobian that multiplies the delta of post parameters of time t minus 1, delta of post parameters of time t, and delta of post parameters of time t plus 1. And the Jacobian matrix here is the positional Jacobian matrix that maps increments in parameter space to increments in the vertex position where the sensor is placed, right? So when we multiply this Jacobian times these deltas, we are obtaining how the error in acceleration consistency increases or decreases as a function of delta x. Okay, good. So now we need to optimize over a batch of frames. So I pose a question. If the error residual for one frame is n, and the number of post parameters is p, how large is the Jacobian of the residuals for all frames? Right? So if for one frame we have n residuals, now for t frames, we will have n times t residuals. So I'll have many more rows in the Jacobian matrix. How many parameters do I have now? Before I had p for one frame, but now I have t frames, so I'll have p times t. So I have like a much bigger t squared bigger matrix, right? Because I multiply each dimension by t. So that's expensive in general, and you need to exploit the diagonal structure of your problem. So if you look at the Jacobian matrix, like you basically realize that the orientation term is essentially it only depends on the current frame, right? So here we have a Jacobian matrix which has zeros on the diagonal and has like these block diagonal terms. These Jacobians are the Jacobian at time t minus 1, Jacobian at time t, Jacobian at time t plus 1, which multiply the corresponding delta x of t minus 1, and delta x of t plus 1. So the orientation terms, there is no coupling across time We're not measuring, how the orientation in t-1 matches the orientation in t+1. And that's why you have this block diagonal thing, which makes this, this system completely diagonal. So the time frames are completely independent. That's why you have this system, which is also like independent of each other. Now, the acceleration residual terms are a bit different because the acceleration residual terms do link different poses, right? Because to compute the acceleration, I need to know the pose at t-1 and I need to know the pose at t+1. And that's what is reflected by this other block diagonal thing, which links t-1, t, and t+1. But still, it's very sparse. I'm not linking t+1 to the first frame of the sequence. And this allows you to solve this much more efficiently. And in fact, the slow part of the algorithm is not solving these linear systems. It's rather updating the model. So when you have an optimization problem, it's good to think about the structure of your Jacobian matrices if you're using like a quasi second order method like Levenberg-Marquardt or Gauss-Newton. All right, so exploiting these properties and using this optimization. The cool thing is that for the first time, it was possible to recover like these nice results of human motion from just a sparse set of sensors, right? So I remember looking at these results and like thinking, okay, like there must be something wrong in the code because like I cannot believe that we can get this accuracy with just six IMUs placed on the body. But this is like by using this batch optimization and using a strong body model and priors, then you can recover and deal with a lot of ambiguities, right? And this is cool because now you can only like, you can place like just the sensors at the body parts, and then you can obtain these results. Yeah, that's the cherry on the cake. Like basically we had like the first author of the paper write Eurographics, which was the conference where this work was submitted. We made him write Eurographics on the whiteboard, and then using the IMU measurement, we could recover the handwriting. So it's not perfect, but it's remarkable that we can get this accuracy. All right, so now the evaluation, like on the left, you have this model that is based only on orientation consistency. And on the right, you have like the full sparse inertial poser, which optimizes over all the frames and uses also the acceleration. Again, if we had integrated acceleration by going from acceleration to position and integrated this in the optimization, things would have worked much worse, right? The key is to predict acceleration and have the objective terms in the measurement space with as little processing to the measurements as possible. All right, so we also validated on a data set where we had 4 actors, 5 activities, 8 synchronized RGB cameras, and 10 IMUs. And we used 6 IMUs for tracking and 4 IMUs for validation. And we see here the angular errors, and we see that the orientation only measurement has like 19 degrees. By the way, this 19 degrees is not that bad, actually. Like this metric is pretty hard, right? I mean, very soon, because it's not a planar rotation. What you're measuring is like rotation between 2 coordinate frames. And so an error of like around 10 is pretty good. Okay, so we have the angular error. This is an interesting comparison of SIP minus M. SIP minus M is using the SIP, what I described, but instead of using the simple model, we used like one of these manually rigged models that we were using in the past. And the error is significantly worse. We have 18.24, whereas with SIP, we have 13.32. And I think one reason is that the actual skeleton of the simple model is predicted from the surface, and then the acceleration measurements can be better predicted with the simple model, and the orientations also can be better predicted. So that makes the whole thing better. So SMPL not only makes the process of creating the body model automatic, but also it turned out to lead to better performance. And here's the performance in joint position error. And again, like the trend is similar, even like the improvement is more drastic. So here 3.9 centimeters, that's pretty accurate, I think. All right, so limitations are that the hand and the feet were not tracked. It's a problem that we still haven't solved, how to track the hand and feet if we don't see them. But it would be interesting to, for example, reason about interactions with environment in order to solve this problem. We also do not deal with drift in global translation. So the optimization does help, but still when you numerically integrate over long periods of time, like things tend to drift. And it requires a model of the person, and it's an offline approach. So you need to see all the measurements and then optimize all at once. All right, so these are some of the limitations. And so notice here that the hands are not accurately tracked. All right, so the conclusions are that this was the first work to demonstrate that with 6 IMUs, you can reconstruct the human motion quite accurately. It can reconstruct arbitrary motions, and it enables motion tracking in the wild. I mean, these are the computation times, and the actual time is not that important because this was an implementation in MATLAB, and this can be made much faster. But the relative times are important. So here, like the model update is like given once you figure out what the increment in post parameters should be, like to update the mesh to produce the new mesh or the new joints, that takes actually 14 seconds, which is significant because look, setting up the Jacobians, these were like basically they were implemented by ourselves, like the Jacobian matrices. This takes 3.3 seconds per iteration, and solving the system actually takes the least time, like 1.5. So these large, sparse linear systems can be solved pretty quickly. So here, this is showing that the model update is actually the bottleneck here. All right, so how else we can use IMUs? Well, one problem, which we mentioned in the previous lecture, is that the data sets with in the wild images and 3D poses, there are no data sets. There were no data sets in the wild with accurate 3D reference poses. So we decided to use this setup of a sparse set of IMUs on the body and a handheld camera from a phone in order to obtain a data set of humans with in videos, right, in challenging scenes, paired with good reference poses. So we are solving this another combination of video and IMUs, like some of prior works that had been shown, like including the work in my PhD thesis. But here we want to use only a single IMU camera. A single camera. And this makes the problem much more challenging. So the first thing that we realized is that if you have a video, the first thing is that if you're tracking, for example, like 2 people, you have many people, right, detected in the video. And the first thing is you need to associate what are your models with the correct detections in the image. And this assignment problem is actually quite tricky if you have a lot of people, as you can see here. Then you have to solve a joint optimization problem over the full sequence to make the models consistent with the orientations and consistent with the 2D detections. So like we have an algorithm that measures like over time using a multiple assignment problem algorithm. We assign the 3D models to the correct 2D detections. And so you can see here all the detections, and here we can see the associated 2D poses, and then we can optimize the model over the poses over all the frames to match the detections and the orientations and accelerations. And I'm not going to explain all the details. This would take too long. But the cool thing is that, you know, using this, we could record sequences in Tübingen, for example. Like this is a collaborator of mine, or a participant that was like doing the groceries, and we were capturing these sequences like in natural environments. And these poses on the right, you can see are quite accurate. And now this data set is actually widely used to evaluate human pose estimation methods in the wild images. And what is quite cool is like that if you animate the scan, including the texture, so you can obtain pretty realistic results, actually. Yeah. So here's just taking a scan with the texture and animating it with the reconstructed results. So this data set is available on our website. And so if you're working on a project that has to do with 3D human pose estimation, it just makes a lot of sense to check this data set to evaluate your method. So this data set contains 60 video sequences, 2D pose annotations, 3 reference poses, camera poses for every frame in the sequences, and 3D body scans and 3D models for the subjects that were captured, and 3D models in different clothing variations. All right, so this is all for this lecture. We have like the video you can check of this sparse inertial poser if you're interested. And if you're interested in checking more IMU-based tracking methods, you can follow this link here on the section, research section, human motion from wearables. Yeah, thanks for the slides. Like for the slides, I based some of the slides on the paper by Richard Hadley, IGCB, I think it was 13, not 14, sorry about this. And the slides based on SIP and 3PW papers. So for this, I thank Timo von Markart. All right, thank you. That's all. Bye-bye.